Hello everybody. I wanted to make a short video about naming hydrocarbons. Well, let's say that you're given the following, and you're asked to write the name of C5H8. You are given two tables that are going to help you name hydrocarbons. One of them is table P, and the other is called table Q. And here's the relevant information on them. Ta-da! Notice table P identifies prefixes. These prefixes in the name of a hydrocarbon will tell you the number of carbons. If you see meth, that means that you have one carbon in the main chain. Eth has 2, prop has 3, but has 4, pent has 5, hex has 6. There's also hept, oct, non, and dec. But I'm just going to work with these. Then you're also going to need to be able to tell whether the given hydrocarbon belongs to the alkane family, the alkene family, or the alkyne family. And you do that by matching up. You see which of these three general formulas will produce the given hydrocarbon. Well, let's start off with table P. Because I have 5 carbons here, that means that the name obviously has to have pent in it. Well, what does that mean? Does it mean that I'm dealing with pentane, pentene, or pentyne? Well, we have to go now to table Q and match up the relevant general formula. Well, how do I do that? Well, if I have 5 carbons, let's say I'm just going to try this out blindly. Maybe I think it's an alkane. Maybe I think that this formula corresponds to the specific formula. If I have 5 carbons, if n equals 5, well then, H should indeed be equal to 2n plus 2, which is 2 times 5 plus 2 is, 12. No. Clearly, this is not an alkane. Is it an alkene? Well, let's try the CnH2n. Well, if I take that 5 and I put that here, well, 2 times 5 is 10. No, it's not an alkene. Well, that leaves an alkyne, but let's see why it is. CnH2n minus 2. Well, if I plug 5 in for the number of carbons, and I say 2 times 5 is 10, minus 2, that's exactly right. So that means we are dealing with an alkyne, and therefore we call this pentyne. So notice the first part tells you the number of carbons, and the second part tells you if you are dealing with an alkane, alkene, alkyne. Now you might ask, what does that mean? What does it mean to be an alkyne and not an alkene? Well, very simply, and table Q even tells you this. If you have an alkane, notice you have all single bonds. All the carbons are connected by single bonds. If you are dealing, however, with an alkene, as table Q tells you, the sample, notice, has a double bond connecting the two of these. If you are dealing with an alkyne, the sample that they give you has a triple bond between the 2 carbons. So what that means is this is a 5-carbon chain in which you have a triple bond. All right. Why don't you try this one yourselves? Let me clean this up a little bit. And using this information, my friends, why don't you try out C6H14? Try that one out right now. Okay. Well, 6 carbons. I go to table P, and I see that hex is 6. So clearly this is hex something. But the question is it hexane, hexene, or hexyne? Well, we need to pull in our formulas. Now, maybe you're seeing that this number is more than twice that number. So it would make sense that this is your general formula. So it's probably a hexane, but let's double check. Let's do the math as they say. Cn, n equals 6. Therefore, H is 2 times 6 plus 2. Is 12 plus 2? Yes, it's 14. So this clearly is an example of a hexane. What about if I give you a full-fledged structural formula like this? Well, you might think, well, that's even easier, isn't it? Or at least not difficult. One approach that might come to your mind is, well, why don't I just count up the number of carbons? 1, 2, 3, 4, 5, 6, 7. So I have C7, and I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. C7H12. And based upon that, you would say, well, I know that there are 7 carbons, so this is clearly a hept. Notice I added the rest of the table. I felt bad leaving out so much. Now, this, 12 carbons, maybe from our previous practice we'll think, well, 12 is less than twice. So I think it's the CnH2n minus 2 formula for the alkynes. And it is. Let me show you why. C7, well, 2 times 7 is 14, minus 2 is 12. So yes, that's C7H12. So we know it's an alkyne, and that means that I would be adding the suffix of "-ine" to the name. Now, there's a limitation to this method because I know that there is a triple bond somewhere in the molecule. But if I just write the word heptine, the reader has no idea where the triple bond is. Now, clearly, when I write the molecule out, it's obvious where the triple bond is. But how do I communicate the position of the triple bond? Let me clean up a little bit here. Well, whenever you see a structural formula, the first thing you should do is you should number the chain. You should number each carbon. I have 1, 2, 3, 4, 5, 6, 7 carbons. But be careful. I know in English we read from left to right. However, it is possible that you will have to number a molecule from right to left. It depends on this question. You always start numbering from the end closer to the double bond, or in this case, the triple bond. Well, clearly, guys, the left is closer than the right. So because the left side is closer, I'm going to make this carbon number 1. Carbon number 2, 3, 4, 5, 6, and 7. So coincidentally, just as in English, we number from left to right. And this is going to allow us then to say where on the heptane we find, or the heptine, sorry, the triple bond. Well, this is the rule. Since the triple bond is located between carbons 3 and 4, I use the lower of the number to give the address of the triple bond. So 3-heptine means that I have a 7-carbon chain with a triple bond between carbons 3 and 4. Let me give you another one to try for yourself. Okay, my friends, using the rules we mentioned, could you please take a moment and try to name this one? I'll pause, and we'll check in a moment. Take as much time as you need. Okay, so you've finished naming it. First order of business. Yeah, remember what I said. When you see a formula, a structural formula like this, why don't you start by numbering? What end did you start numbering at? Did you start numbering from the left or from the right? Well, you should have, in this case, numbered from the right to left, because notice how this carbon is closer to the double bond than this carbon is. So I do this. 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 carbons here. All right. So again, if I have 9 carbons, that is a non. Now, is it a non-ane, non-ene, or non-nine? Well, if you look on table Q, only the alkenes have a double bond, meaning we're going to put ene here. It is called non-ene, but we need to say we need to state the location of the double bond. Well, it is between carbon 2 and 3, making this 2 nonene. Alrighty. Let me throw in a word, guys, here. This is 2 nonene. If I were to move that double bond, let's say from between the second and the third to between the first and the second, say I move that, and I did the following, change this a little bit. So I put my double bond here, bring that up, and there was a carbon there, 3, 4. Here we go. So this is 1, 2, 3, 4. This molecule, by comparison, would be called 1 nonene. Now you might ask, well, if they're both nonene, does that make them identical molecules? No. These are slightly different compounds. These are called isomers. When you are isomers, notice you both have the same molecular formula, 9 carbons, and we have 18 hydrogens. So they both have this in common. They're both C9H18, but they differ in the placement of the double bond. 1 nonene has the double bond between carbon 1 and 2, whereas 2 nonene would have the double bond between 2 and 3. Okay, so that was my little lesson on naming what we call single-chain hydrocarbons. In my next lesson, I'll talk about drawing single-chain hydrocarbons. Thanks and bye-bye.